Hello, good afternoon. We start today our last lecture before Easter on fundamentals of material science. We try to complete, at least in principle, the discussion about metals, much more to say about course. And we will come back to metals at some stage by dealing with other materials, therefore polymers, ceramics, composites, natural materials as much as possible. One of the things we all know about metals is that they are conductive. And we assume also one other thing, which is not obvious as it may seem, is that if the materials are electrically conductive, they are also thermally conductive. In fact, this was reported also in a chart by Michael Ashby and his collaborators. We present from time to time some of the graphs from Ashby. You will find several hundreds of these because they investigated most properties of materials. In principle, these charts are intended for materials selection, which means that I have an application at a temperature in an environment, and I would like to find which might be the best options in terms of materials. Here you can see that we have electrical resistivity, which is the opposite of the electrical conductivity, as you may know, and on the x-axis. And on the y-axis, you have thermal conductivity. What is obvious from this chart, even at a quick look, is that metals present a kind of relation between these two properties. And in fact, you can imagine there is a coefficient. This graph is at room temperature, ambient temperature, so 20 degrees Celsius. And you can easily see that, well, some metals are more conductive from the point of view of temperature, so thermally conductive, than electrically conductive with respect to others. But we can see that in general terms they can be arranged along a line. It's obvious. Well, you can see that the resistivity of copper is lower than the resistivity of titanium. In fact, you see copper wires for transporting electricity, and you don't see titanium wires. And well, which finds an explanation from these properties. This applies only to metals. You may suppose that before you go to look into this matter, that this might apply to other materials, also the non-conductive ones, the insulating ones. In engineering terms, please remember that there is no there is no separation, in fact, by the fact of being conductive or insulating. It's just a convention. In reality, you have better conductive material and worse conductive material. Of course, you have a lower, considering with, for example, stone or glass and so on. Of course, they are not considering electrically conductive and even not thermally conductive. There is worse than that. For example, foams, which are at the bottom, and natural materials are used to be insulators like coal. What is important is also the shape of these regions in which a material is included. This is very important in material science terms because it communicates the range between two values, which might be quite far apart in some cases. You might see also, for example, that you have silica glass. Silica glass, it may range, of course, it has a very high electrical resistivity, but this might range by 4 order of magnitude. It goes from 10 to 24 and 10 to 28. Which says a lot. Apart from all the details, as always, is not the question of remembering the details, because you might have forgotten next minute what is exactly the electrical resistivity. It's important of a material. You may also look at that, but it's important to see what's the point of disposing the material in this way, to try to understand what is the deviation, the range, and in which property you have the higher range. And this might be also of interest. In some cases, for example, with stone, you have a quite considerable range, and also in silica glass, quite considerable range of electrical resistivity and therefore of electrical conductivity. But as for thermal conductivity, they remain about at the same level. This can make consideration from the design point of view, on which I don't expand, of course, because it depends what you are trying to do. But this is important because it's a way you are able to design with the material. That's the approach that allows you to design. Then the last thing I would say on this graph is that the characteristic of the study that Ashby has been doing for over decades, is that it considers also natural materials, some of which are traditionally used, like wood. Wood is a construction material in the fullest sense of the word. Other materials have been used not as materials as such, but as covering other materials. And anyway, they provide some resistance, some mechanical resistance. This is the case for cork. Leather has not been used, has limitedly been used in engineering, but it has been used for a number of commodities, which enter the field of design. Design doesn't only involve the design of a big structure like a bridge or a house, but it might also involve especially in modern time, the design of a small item like a bag, and the bag can be done in leather, or a shoe can be done in leather, and forces are applied also in that case, and the materials need to withstand to these forces. And the materials can be replaced. I may consider making a bag instead of leather with another material, a plastic material, say, and I have to make considerations. That's the point of including all the materials, not just very important and noble materials. There are no noble materials and less noble materials. All materials are on the same level, because all materials can be used for design. Now, this becomes even more important when you talk about sustainability. Now we design with waste. And waste is even more difficult than these materials, which at least have a kind of tradition in being used. So we know a lot about this, even if we didn't do houses with leather, but we know a lot about leather because we are using it since 2000 years and more. Okay, so we were talking about steel, so about the iron carbon diagram. You may remember you had in the last lecture, and we discussed a lot about it. You may remember, I just remember some little things, that we have two main form of iron, so iron alpha and iron gamma. Iron alpha, which is the structure is ferritic, and it's cubic body-centered cubic, and whilst austenitic gamma iron is face-centered cubic. Then the structure, these are the two structures which are present when you have just iron and carbon, and some amount of carbon. The amount of carbon can be from almost nothing to 2.06%. Let's say 0.01 to 2.06%. In practical terms, most steel are concentrated below 1.2% of carbon, between 0.03, 0.05, and 1.2. So you have different classes of steels. There are entire books about this. I wouldn't know, but there are, well, of course, classifications, and you find everything about this. It's important to understand that there are a few elements which have an influence on steel, which are in particular chromium and nickel. These are the two main actors after carbon. Carbon is inherent to the fact that iron becomes steel, and then if you have more carbon, you have cast irons. But let's concentrate on steel. Here you have ferritic steel, which of course has got a alpha iron phase prevalently. It is not the case that ferritic steel has 100% ferritic steel, alpha iron phase, but it has mostly alpha iron phase. And as the consequence, it has it is also resistant at high temperature, and it might become sensitive to crack propagation. In general term, they are less tough than austenitic steel, which is the other category, because the structure, the lattice, is less concentrated, is less packed, and in general they are less resistant to wear and to the crack propagation. Although they can go up to high temperature. Please remember one fact, that steel doesn't, and materials in general, doesn't only come to high temperature for production, but there are a number of services in which materials are required to go to high temperature. For example, for doing molds to cast the material, to produce the materials, and for example, for applications in which it is intended that hot water, but even worse, hot oil or vapor at high temperature have to go inside, for example, tubes. Then there is the main question of corrosion, which we have treated last time. Corrosion, it doesn't tend to be a big problem in ferritic steel, unless there are environments in which there is lots of chlorine. Lots of chlorine can happen. This can happen at sea, or this can happen by treatments which are required with especially alkaline treatments, like with sodium hypochlorite, or in operation in some situation like in refrigeration, where chlorochlorine carbides are used. So there are a number of environments in which chlorine is involved. In that case, ferritic steel might have some problems. how much chromium we need to have a ferritic slip for chromium to be effective? Well, not less than 10%. Then the range is usually between 10 and 18%. In some cases, you go up to 27%. And in other situation, you would expect that you are just comparing at the beginning in the iron carbon diagram. We were just comparing the situation without involving nickel and chromium. In other situations, as I was saying, we need to concentrate on the fact that chromium and nickel, here in stainless ferritic, there is little nickel normally. In austenitic, there is a substantial amount of nickel, as we will see. So we need to make a sense of what happens when chromium is introduced in iron. So this is a chart which represents iron and chromium without considering the fact that there might be carbon. We may, for a first assumption, to say that carbon is absent. In reality, in some cases, for some irons, alloys, carbon might be almost absent, so we may have a very limited content. This is the situation with iron, chromium, and no carbon. You might observe a few things. First of all, since that liquidus curve, the curve which separates, you might have a solidus, which is the curve, the lower curve, and the liquidus, which is the higher curve. In reality, in contrast with what you say at school before entering the university, there is not a precise melting temperature. There is not an exact melting temperature, unless you have just a pure crystal. Instead, you have an interval in which, in this interval, you have a small range where melting starts, and then where melting is completed. That interval might be small, as in this case, or larger. Anyway, you can initially observe the fact that chromium, pure chromium, which is used very limitedly in industry, pure chromium has a higher melting temperature than pure iron. Therefore, when you start adding a substantial amount of chromium, the temperature goes up, but you need to add 40 or 50% of chromium. And this is not usually the case. Why so? Because you can see the sigma region, the kind of ellipsis, which is between around 47.2 chromium weight, and around that region, and from around 450 degrees and 830. And you can see the sigma, it's an intermetallic, and it's something which is to be avoided. Because it's not an alloy. There is a lot of discussion about the fact that it's going to be called that intermetallic exists in the first place. But what happens in practice is that you don't have a real alloy. You have a kind of solid solution that melts as a whole, and that behaves as a whole. And in practice, what happens in practical terms, we will see it a bit later, but it represents a limitation to the ability to use that alloy, because you have really, if there are ranges of intermetallic, into the alloy, it is difficult to work the alloy. And please be aware of the fact that you don't need to be at 45% of chromium to have the intermetallic. I mean, in the whole of let's consider the alloy. You want to make this. You have this. You're working your alloy. You may not need to get as far as 45% because we are making an assumption which is not true. That if you have, for example, 18% of chromium, which is a typical situation in steel, we have 18% throughout the whole of our alloy. In reality, the amount of chromium might be variable across our material. And in practice, we might have the formation of some intermetallics in some places, which reduces the resistance of our alloy. As a matter of fact, for example, having 27% of chromium as in one pure steel categories like the IC 14444, it becomes a bit tight, a bit too close to the presence of the intermetallic. Apart from that, I will come to that back later. There is also need to see that in this iron chromium diagram with no carbon, we can see that the gamma area is a very small one. It's a very small one, and we easily come out from the gamma area when we apply, say, 18% of chromium. That's also why the area is that one. In reality, the range we are using in chromium is between 18 and 27% in most cases, because we are a little bit far from the gamma area and a little bit far from the sigma area, because we want a ferritic, if we want a ferritic steel. On the other side, what happens with the introduction of carbon is that the gamma area and alpha plus gamma area, it's expanded. There is which is the alpha plus gamma area is that small one between 11.2 and 13.4, and it's not marked because it's too small. But it would expand if we put more carbon. It would expand, and in practical case, we might have a mixture of ferrite and austenite in some steel due to the presence of more carbon. I hope it's not too confusing, but I will come to that back later. Anyway, this is without carbon. If we have more carbon, then the alpha plus gamma area is expanded. And in practice, a mixture of ferrite and austenite is more possible, even if we don't have nickel. After that, we need to consider what is the exact effect of intermetallics, of sigma. Here we see the sigma phase forming in between in an IC 316, so 18% of chromium, very little nickel. Even so, we have the formation of that sigma phases, which in practical terms creates an accumulation of chromium, which creates problem of corrosion, because we needed to have 18% of chromium in stainless steel to avoid corrosion. And a little bit similar to the intergranular corrosion, but it's worse because the amount of chromium that we lose is considerable, plus doesn't make the material ductile. It has an influence that corrosion hasn't. So the material, whilst the material in most cases can be worked even with corrosion, in this case it has difficulty to be worked because it loses ductility. In practice, it is not able to plastically deform without destroying it. You can see, as always, the X-ray diffraction curves, which shows you what is the situation. You have some peaks. Of course, the highest peak is for iron. We can suggest that two peaks relevant for irons are two different iron phases. I might suppose that the highest one is an alpha iron and the lowest one is the gamma iron. Then there is chromium, and the chromium, when I don't go into details with chromium, but when chromium is so high, this represents that small area, the area of the intermetallic, the chromium amount is going to be 40 or 45%, so a lot. And also chromium has got two possible phases. Then we have nickel a little bit and molybdenum. The presence of intermetallics, it's a research subject which might be of interest, of course. And intermetallics are not characteristic just of steel. They are also possibly present, for example, in aluminium. Here we have an aluminium alloy 2024. We'll have a look at aluminium later on after Easter because, well, of course, aluminium is a metal, but talking about aluminium will introduce us to a different behaviors than the one it's characteristic of steel. So in terms of ductility, of crack resistance, and so on. But aluminium alloy 2024, it's an aluminium with the second alloying element, which is copper. It's a series 2 aluminium. And you can see here that they have some kind of intermetallics, which are represented in that area. And when the alloying is quite complicated, we have three types of intermetallics. When the alloying is, the details are not that important, but the question is that when the alloying is complicated with a number of actors present, it might degenerate intermetallics. So some parts of the metal that behaves unlike the rest of the alloy, and basically they are able to melt or solidify on their own, which you might easily understand represents a problem in terms of workability, because in the end it has different properties, different characteristics. It's like when you're trying to make a cake and there is a harder bit of the cake. For example, because there is an agglomeration of flour and so on, and in the end it might happen that this part has to be discarded. And that's what happens with intermetallics in very practical terms. Having discussed all this situation, it's easy to understand that for austenitic there is not much difference, apart from the fact that we introduce nickel as an actor, and nickel as in amounts which are not very low, like in ferritic, where nickel is more as an accident than as a real actor. And so we have 18% of chromium, but in this case we have, which is a typical amount. In this case we have 18%. In ferritic you could go as down as 10% of chromium, depending on the other elements. but in this case we have 18% of chromium and 8 or 10% of nickel, which are the typical two steel, two ISIS series 304316 steel, and some molybdenum, and again in both cases, again carbon content is very low, and the fact is that here you have the amount of chromium which allows you to have a passivation, so the formation of a thicker oxide layer, which is able to protect what is below it from corrosion. It is important to consider that you can have a higher toughness. In practice, the cracks are not able to expand very much. They tend to be quite restricted in their growth. So in practical terms, it is resistant to defects. You can have graphs also that show the effects of both nickel and chromium, like you see that graph to the left. In practical terms, we have a large area which is for austenitic steel. When there is a substantial amount of chromium, you have austenitic steels. As always, as also in this case, we consider a very limited amount of carbon. This graph was done considering a 0.05 carbon, very, very little carbon. So carbon is almost negligible on this graph. So with this graph is about nickel and chromium, but in a iron context. So the bulk is iron. We don't consider the other elements, and this is a simplification which is a bit debatable, but for initial purposes, it's fine. It gives you an idea that if you have little nickel, you have ferritic steels. There are some regions in which you can even have martensitic steels without having any heat treatment. If you don't have nickel or chromium, you don't have martensitic steel if you don't have a heat treatment. Here, even without any heat treatment, you have some regions in which there is martensitic steel. And then there is a precipitation hardening steel. This involves precipitation hardening steel involves instead heat treatment. So in all other regions, you don't necessarily have a heat treatment. For precipitation in that area, which is you can see that graph, it's a kind of industrial graph. It's not that precise, but it gives you the idea that you can be able to precipitate the particles. So mainly carbides, you are able to precipitate a little bit of carbides, and you can have a harder steel with the precipitation of these carbides, chromium carbide, and also nickel carbide. So although in most cases chromium carbide. You have harder steels, but in that case, but which might be prone to corrosion. Then you can have a category which is that of doublet steels, which have a considerable amount of chromium, more than 18%. Doublet steel starts at 18%, roughly, and they include even nickel, and in practical terms, they are used for low temperature resistance. For low temperature resistance, because they tend to compensate the two effects, because if there was only austenite would deform a lot, ferrite would be prone to stress corrosion. Having both of them compensates for this, because consider that steel is also used at a very low temperature, for example, in refrigeration, and therefore that withstand that. Although duplex steel is not yet cryogenic, there are also some steels, I don't go into details of everything, that have also a cryogenic effect that can go even further, possibly to work with in atmospheres with liquid nitrogen and so on. A refinement of the graph I showed you before is the so-called Scheffler-DeLong diagram. That graph, the previous one was a quite industrial one, which was intended to show to the layman where in each kind of steel, so magnetic, ferritic, and so on. In that case, we are more precise. You can see that the style is different, and we are more precise in terms of martensite, austenite, and ferrite, and so on. So we can say where ferrite starts, and when ferrite has completely taken place of austenite, when we have 100% of ferrite. We have at X and Y axis, we have the chromium equivalent and the nickel equivalent. We can consider that some alloying elements, because silicon is not a metal, molybdenum is a metal, niobium is a metal. Silicon is not a metal, silicon is a ceramic. And then we have it's a non-metal and creates ceramic materials. Silicon oxide is the first. It's the paramount ceramic material. Then we have the nickel equivalent, which is when we have, of course, nickel, and we add carbon and manganese. So manganese can expand the gamma area, so it's on the side of nickel. Molybdenum, silicon, and niobium expand the chromium area, so they are on the alpha side. So some are called alphogen, and other ones are called gammogen. So there are some that expand in austenite area, and others that expand the ferrite area. The first are called gammogen, the other are called alphogen. As I already mentioned, martensite can be present. There is not much difference with what we have seen last time. It's more precise, and these commercial categories are not indicated. So these are commercial categories: precipitation, hardening, and duplex steel. But it's important to know them because in practice they correspond to the physical reasons: the precipitation of particles and the presence of austenite and ferrite. There is not much difference because you can consider that the duplex are to the right, and the austenite to martensite are the precipitation hardened, roughly. But anyway, this predicts almost everything about austenite, ferrite, and martensite, the three fields. Apart from the fact that we don't consider nitrogen. I was talking before about liquid nitrogen. Nitrogen enters in a number of situations of in steel, and in some cases it's also put in steel to create, for example, some surface layers to have even better withstand, not only withstand corrosion, but to improve the hardness, to improve substantially hardness. And therefore, in this graph, their nitrogen is not considered. because it is a bit troublesome, because then you can have some acid nitrogen, some basic nitrogen, depends on the pH, and therefore there are a number of considerations to be made, which is possible for a simple treatment of that causes even too much. Austenite and martensite are not confined, are not just typical of steel, because, for example, the transformation the austenite-martensite transformation is at the basis of a phenomenon which has been studied a lot since the 90s, which was discovered by chance, and it is connected with the so-called nitinol, the nickel titanium alloys, which are roughly 50-50 nickel and titanium. Equimolar alloys. But apart from that, and the presence of possible other elements, what happens in that allows shape memory is that austenite can be transformed into martensite by heating and cooling. That transformation, as always, takes some time, so there is a martensite start and a martensite finish temperature, and conversely, there is an austenite start and an austenite finish temperature. The effect of this is that the material has two different lengths, two different geometries, a geometry at high temperature and the geometry at low temperature. And so it has two stable situations. One is austenite and one is martensite, because the relevant fact that the deformation allows to change the length, passing through a phenomenon called twinning. The twinning means from twins. Basically, you have two different layers that glide one with respect to another, and that gliding allows finally to have this kind of extension, this kind of tetragonalization, where it becomes tetragon with respect to the initial structure of austenite, which was cubic, and cubic at centered faces, face centered cubic, and therefore the length changes. And you can have this also in two ways. You can repeat the cycle a large number of times, and you do this kind of training. So you have each treatment, basically. You repeat it a large number of times, and in the end, the alloy remembers that at low temperature it needs to be of one shape, and at high temperature it needs to be on another shape. In practical terms, it is you don't need a mechanical loading, but just heating and cooling, and it has two different shapes, two different geometries. So you apply that training with some mechanical loading, because you remember that you could also use the transformation into martensite by an adapted mechanical loading, a kind of plastic deformation induced transformation, which is something which is done also in metals and in steel, and of course at that point you have two different shapes, two different geometries, which can be retained at low and at high temperature. This is useful, for example, when you need to heat something up to close it or to open it. This is a principle which is of interest. The only problem is that the cost of these devices very high, but this is applied, for example, for earthquakes when you need to open it or to close it, and you just need to apply a deformation. It is you induce a deformation by just heating or cooling it, and because it changes the shape. This is applied a lot with plastics. With plastics, the problem is that it's usually not reversible. In this way, it is reversible because it is both situations are thermodynamically stable, and so in the end you can remember both of them. Martensitic steel, well, there is much difference apart from the fact that they are harder, more brittle, but they are used for smaller dimension items, which need to be stronger also on their surface and to withstand different types of loading. So in practical terms, martensite is able to offer that hardness and large strength, withstanding different types of forces, and you make small structures. You usually don't make very large structures with martensitic steel, because not just because of the cost, because of course heat treatment would require some more cost, and then you need to add other elements. Usually you have always likely not large quantities and molybdenum, and you have also a larger amount of carbon. Carbon in this case is not very close to the lower limit, but you have carbon around 0.9%, so around the eutectoid. It might be very low, but there are also here there are a number of categories, but in general terms you can also go quite high. You can have also iterator eutectoid steel. You may remember the eutectoid point at 0.9 and percent of carbon. So they were subjected to heat treatment, also to repeated heat treatment in some cases, and they are used for small structures. It is interesting that this kind of you will find this kind of graph, this kind of diamond graphs, which are of interest because you may consider a number of properties. You may consider a number of properties and to evaluate against each other. As I was saying, the martensitic, like it is the case for shape memory alloys, you can induce plasticity by a transformation, or conversely, you can. There is this change, this exchange between mechanical deformation and thermal transformation, which is the same that happens in shape memory alloys, with the fact that here there is no irreversibility. There is no reversibility in the sense that you would need change the structure. You would need to melt another time your material. These properties, for example, are, well, I show this because these are some properties which are essential in steel. Tensile strength, well, there is not much to say. Notch fatigue strength means that you have a cyclic loading, and so fatigue, as we were saying last time, for a large number of times in a large number of cycles in a short time. So you have a kind of calculation of the expected life of an accelerated aging of wheel with notch. with notch, because you remember notch means a defect. You create defect. To show whether, for example, you may remember the fatigue limit, that there is a fatigue limit for steel. The fatigue limit does remain or not for a definite number of cycles. Of course, you cannot do an infinite number of cycles, but you can measure a service. For example, you can consider that your structure needs to withstand 1 million cycles. During its life, you perform 1 million cycles at a low load, and you see if you undergo fracture or not. And so that if there is a fatigue limit, despite the presence of the notch or not. Then you have toughness, so you study the propagation of the crack, and you have impact. You study the propagation of the crack. Once you impact, you basically drop a hammer, like in Sharpie test, which we have seen a few lectures ago, and if you are able to break, and which kind of energy it absorbs. Then you would like to see other properties, in particular, if it has a kind of resistance, even in presence of defect, and if it is able, if it is going to break suddenly, or if it's going to give you some indications of failure. So if the failure is going to be abrupt or not. So these are the factors which you study to see if there is a point to have a transformation using plasticity magnetic. So if you do in practice, what you do is you apply an external stress, and whilst you perform that phase transformation. So you transform it from austenite to monazite in applying also an external stress, so inducing the twinning, etc. So what does it mean in practice? That you improve some of these properties, you improve all of these properties, some more, some less. And for example, you have important property, which is the property of carburizing. Carburizing, it's like what we were discussing before with nitrogen. Nitrogen is you can prepare your steel in presence of nitrogen, so that it is covered. Nitrogen doesn't enter the steel, but it's mainly on the surface, and it provides you with larger hardness. Carburizing is done a lot. For cutting devices, and like knives, etc. And saws, teeth. And it provides you with a local hardness, which is much higher, because basically you prepare your synthetic steel in an atmosphere. You burn in presence of charcoal, and therefore charcoal, carbon particles enter the surface. This is a quite old treatment. Now it's much more performant with nitrogen, to prepare steel in an atmosphere filled with nitrogen, and therefore allowing the nitrogen to enter the surface, providing you with higher hardness. If we have more than 2% of carbon, 2.606% of carbon, we have cast iron. In historical terms, we had first cast iron and then we used steel because we were not able to alloy it very much with chrome and nickel and so on, and therefore not much able to provide drawing and other operations. Extrusion, very difficult to, well, you can cast also tubes also with cast iron, but they are going to be very thick. It is not much attached by corrosion. Cast iron has a limited attach for corrosion. It is created in large thickness. Here you can see, for example, this is the weight which is under even not only street lamps, but also home lamps, which provide structures which might be even complicated, even artistic in some cases, but thicker. And the characteristic is that it is very fluid. It is reasonably fluid when molten, and not only you have a fluidity, but you have also a compactness, which allows you, in fact, to make these complicated pieces. You have the big questions in cast iron, looking at big research teams, is the presence of carbon. Of course, you have a substantial amount of carbon because you go from 206 to 4.5%. Theoretically, it goes up to 66%. But in reality, there are not much cast irons which get to that point because they are then closer, very closer to a ceramic one. It is interesting that well, the main question is how carbon is disposed. You have this kind of nodules which might be intercalated into the iron structure, and there is also another element, another actor, which is silicon. Silicon is there. Well, it's there from the beginning, I would say, because when they started producing iron, they produced iron which was cast iron, basically, because they weren't able to reduce carbon that much and obtaining something which was suitable for any application. Was cast iron, and there was the presence of a substantial amount of silicon. You can have, though, a cast iron with more silicon and a cast iron with less silicon. The gray one, it has around 3% silicon, and the white one is a more refined product and has less. It is interesting also the shape that graphite assumes, because graphite can also accumulate into interesting shapes, which unfortunately normally compromise the resistance, also the resistance to corrosion, but of course also the purity of the casting. And of course they are not detrimental for hardness, but they make cast iron even more brittle than it is already. That's why they also do very high thicknesses, because then it's over-dimensioned, even in case of impacts. In fact, there are architectural structures made in cast iron that have lasted over the last 100 years, which is not always the case with steel. But apart from over-dimension, it's interesting that you can have nodules and chunky cast iron, this position of graphite into cast iron. In mechanical and in duration terms, the nodular ones would be more preferable The other ones even more increased bottlenecks. It is interesting also that graphite tends to concentrate also in very complicated ways, tends to penetrate. What, in practice, what happens is that when iron melts, graphite carbon has not melted yet, and in practice is able to enter to filter across um, the molten iron, and in practical terms, it enters also in quite complicated ways, quite complicated ways, which might be always connected with the principle of lower energy. So that's why it takes this kind of style, which compares to the so-called the Fibonacci styles, because it is the lowest energy. It's not that they want to behave like broccoli. The question is that there is a lowest. This is the lowest energy situation for development, for in this particular case, entering iron. Of course, if we are able to control the cooling down during melting, then we would prefer to have some nodular parts, which are less detrimental for mechanical properties and don't increase that much mobility. Please be aware that apart from cast iron, etc., this can be of interest, for example, for also in other cases with composites. It's very important that the particles tend to aggregate, to coalesce with each other, or not, or that they are able to deviate to cracks, for example. So this is a general concept, and of course this cannot be. This is an alone, not a composite, because in the composite, what carries the largest part of the weight is the reinforcement. In this case, it's not carbon doesn't take the maximum, the major part of the force. The force is withstood by iron. Then carbon gives other properties like hardness, etc. But it is the diffusion of particles and the uniformity of particles takes a role in the quality of the material in general sense. So the origins of cast irons, this would need lots of time to be explained further, but it's just for the sake of curiosity. In the beginning of 19th century, of the end of the 18th, beginning of 19th century, some big structures were built. For example, the first vapor engines, the first steam engines, for example, by Stephenson and so on. So 19th century. Were made basically in cast iron, which was wrought by pig iron in reality, because it wasn't really cast iron, because it wasn't the difference between the wrought pig iron and the cast iron, apart that the amount of carbon is substantial, so we are in the region of cast iron. But it was pig iron because it wasn't done in proper molds. It was done in sort of molds which were artificially created, artificially obtained more than artificially created, like it was, and this resembled the device where pigs were going to drink, the kind of canals in which it was made flowing that iron, which then solidified in some way. So the result of this is that the shapes weren't precise. But despite of this, then they started obtaining some kind of molds to make small pieces like also this. This was really a challenge to do that with the cast iron. Today probably they wouldn't be able to do that because they were making this with small molds, with small um, molds made into ceramic materials also, which in practice were thrown away. So these were unique pieces. In fact, there were differences into their properties. This, for example, is a bridge which is in Belgium near Namur. It's in 1824. It has almost 200 years, and it is studied because it's one of the first suspension bridge, well before the San Francisco one, um, which is a small one because it's above a small river and over a small river, and it's intended for use for pedestrians. It's not intended for use for coaches also. But anyway, in 1824, this was considered every piece was done on his own mold, and obtained from that material, which was solidified in the adventurous way, as it was in that case, with lots of carbon, a substantial amount of silicon still. And although silicon gradually was quite, you could get also to a higher purity. Um, I would end this in remembering, in discussing a bit about the service temperature, coming back to Ashley. You may have realized that these are things which are a little bit, possibly even a little bit too much for a lecture, but service temperature means not the temperature at which they melt, well below that. It's the temperature temperature interval at which we are able to use these materials. This doesn't involve cryogenic and whatever, so we stop at zero. Um, there are some observations to be done. For example, some metals which were very popular, which you could even melt in a pan like lead, but then you have to throw away the pan. But apart from that, lead was very popular, and also zinc. I don't see tin, but tin is also in that area. Anyway, then you have areas which are very large for mild steel, cast iron, and so on, and you see that also the strength is much more considerable. Um, Here, metals are emphasized. You can have a good correlation between a very high um, service temperature, in some cases, for example, with high alloy steel, highly alloyed, so we can have considerable amount of chromium, which anyway increases the temperature, might increase the melting temperature in large amounts, but films are the problem. Then, of course, you have ceramics. You have ceramics of any kind. You have ceramics. In ceramics, the question is mostly about the porosity. You have porous ceramics and not porous and technical ceramics. We will discuss this a bit later on, but you see that the differences are huge. Porous ceramics are orders of magnitude in terms of strength. Although ceramics can be used in um, can be used at a high temperature. Please consider that this is not The studies from Ashby were taken from literature. He was extracting literature from literature, a number of information, for a number of studies, he was extracting information, and these are the maximum service temperature as from a definite study. For example, you might have in aluminium a number of studies which give a maximum service temperature between room temperature and something more. Aluminium doesn't get that far. With titanium, you get that far. With nickel, you get even further. And this is important for production. This is important for creation of mold and for a number of services which are applied at very high temperature. Despite our idea, our common idea, gold has not a very high service temperature. The characteristics of gold are other. For example, electrical conductivity is very good, and preciousness, but on the other side, it has a very high specific weight, gold. What else? I think that we can stop here. You can, the idea of this course, as I was saying, is to create some curiosity about the research teams in material science. Material science is a very large area, and although it appears quite new, you can see that, for example, with surface temperature, you may imagine that there are hundreds, if not thousands of studies only for maximum service temperature for some material, because it is, of course, an important application, an important property to know. Create curiosity about the research teams. After Easter, we will start to see something which is further removed from the ideal. Steel is the most ideal material, and it has quite simple problems. It might have problems into alloying. We have spoken just a little bit of intermetallics. It might have problems into the presence of extraneous substances. Sometimes there is too much hardness in some cases, which leads to brittleness, etc. And this removes a little bit our material from the reality. On the other side, an ideal material would be worthless because, for example, this graph on surface temperature is according to the force applied. If applied a tensile force, if you apply a compressive force, if you apply, in many cases, you apply a bending force, then the material gives its best. So there are materials which are used for one force, and other materials which are used for another type of force, prevalently. And therefore, a material which is good for any force, which is isotropic and elastic in any sense, would have no value because it would have no application, and that we need to relate the materials to their possible application and their possible intended application in the future. Okay, so we'll resume the lectures on not this Friday, but next Friday, which is going to be the 17th at 11, as always. So have a nice Easter period, and see you on the 17th.